Hello everyone, I am Sandra Klar and we are going to get started. I want to welcome you and thank you for attending our second talk for the FY21 NOAA Environmental Leadership Seminar Series. The goal of these seminars is to showcase NOAA's leadership in environmental science by those who lead it and make it happen. I'd like to take a few minutes for a few housekeeping details. First, I would like to thank the NOAA Research Council and the awesome team that I work with in scheduling these seminars, without whom none of these seminars could happen. Hernan Garcia with the NESDIS National Centers for Environmental Information. Tracy Gill with the NOAAs National Centers for Coastal Ocean Science. Katie Rowley with the Office of Ocean and Atmospheric Research and the support of the NOAA Central Library. We also want to thank Kate Becker and Dr. Frank Gallagher, both with NESDIS OSAP, for moderating the questions in today's seminar. Now here are some seminar logistics. Most are listed in the Q&A pod. Please note all attendees are muted, so type all questions and comments into the Q&A box. We will try to get to as many questions as we can by the end of the seminar. We are recording this seminar, and the recording and PDF of the slides will be made available within a few days at the link provided in the chat box. If your system seems to be lagging, please turn off any extra apps you might have on. Also, you might want to watch the seminar in full or larger view. To do this, find the 4-arrow button to the upper right corner of the slides. That 4-arrow button toggles the full screen view on and off. Looking ahead, we have some awesome speakers. Admiral Gallaudet will be returning to our series on December 8th at 2 p.m. You can visit the NOAA Environmental Leadership Series webpage, which is also listed in the Q&A pod. We are working hard to schedule the rest of our speakers for FY21, and you'll find them there as they are entered. Now, speaking of Admiral Gallaudet, I am very pleased to pass the baton to him to introduce our speaker for today. Admiral Gallaudet, the mic is all yours.
Hey, thanks, Sandra. That was so kind of you. And I also want to thank Tracy and Hernan and Katie for setting this up. And I also would like to express my appreciation to Kate and Frank for moderating the Q&A. And but I saw the announcement to this, and first of all, I was very interested professionally in the future of our satellite observing and data information systems that Vanessa will talk about. And I don't do a lot with our satellite programs. I'm mostly focused on the wet side of NOAA, but I did do a satellite oceanography master's thesis at Scripps, so I definitely have a fondness for this and an interest. But first and foremost, I was thrilled to see Vanessa Griffin giving the talk, because I've interacted with Vanessa on and off for about the 3 years I've been here at NOAA, and every time it's just been an absolute delight. Because she's such a wonderful person. She just exudes positivity and a can-do spirit that I know she got from her time in the Air Force, and I just really identify with that from my time in the Navy. But even more importantly, it's her contributions and impact that have been just so extraordinary. So let me share with you a little bit about Vanessa Griffin's just fantastic resume. So she has over 40 years of experience in the federal government, involving research, development, and operations of critical environmental satellites and IT. That beats me by 5 years, and I thought I'd been around the block, but Vanessa more so. So she's the director of NOAA NESDIS' Office of Systems Architecture and Advanced Planning, or OSAP, and she directs the architectural development of the next generation of NOAA environmental satellite constellation. So super excited to hear what she has to share about our future. She's adapting new technology and space commerce business practices to achieve enhanced performance at lower cost. And I know that's been a priority for NOAA leadership. I've been involved with directing that performance improvement. And Vanessa oversees the execution of NOAA's commercial weather data program that's acquiring critical weather data needed to meet NOAA's mission from commercial providers. A real innovative effort that I'd love to see her leadership in that, because, again, it was a priority for us coming in about 3 years ago. And then prior to that, she directed the 550-plus person team responsible for the successful operation of the 18 of the nation's environmental satellites. That's how I first came to know her. And I was just floored by that responsibility and her just flawless performance with such grace under pressure. And so, I mean, these are billion-dollar assets that she managed on step at every turn. Now, previously, she was the project manager for NOAA's largest IT development project. This was the design development of the ground system for GOES, the GOES R series. GOES R was a $10 billion life cycle program. Think about that. That's what Vanessa helped manage. Quite impressive. There really is nobody in NOAA who has shouldered that kind of responsibility. She developed her in-depth knowledge of satellite and ground system development and operations while serving in a variety of positions in her career, including those with NASA, and as I mentioned, the U.S. Air Force. She has a Master of Science degree in Atmospheric Science from Georgia Institute of Technology and a Bachelor of Science in Meteorology and Computer Science. So just couldn't be more pleased to join you, Vanessa. Thank you so much for volunteering to tell us where we're going to go with our critical satellite and information programs. Thank you for being an environmental leader, and thanks for being here today. The floor is all yours.
Well, thank you, Admiral. That was a wonderful, warm welcome. I appreciate that, all the wonderful things. So let's get started. And this is just a conversation. I want to sort of let you know what we're doing as we're trying to map out and start implementing the future of NOAA's satellite observing systems. In my role in that, and the role of my office, which was, as Tim said, the Office of Systems Architecture and Advanced Planning. So jumping right in, so here's what we're going to talk about. First, I want to talk about my office itself and our role in strategic architecture and planning and how we're doing that. Talking about why we continue to focus and need to have our environmental satellite program, a very robust, capable satellite program, and what it does for the nation and all of our taxpayers. And then talk about how we go forward from here. What is our next steps? How we're going to implement the next generation of weather satellites and how we're going to get there. Not only the satellites themselves, but the ground systems as well. And as Tim said, I've had a long career focusing on environmental satellite observations and ground systems for many, many years, and it's just so exciting to be here at the end, really working about and planning and thinking about what we're going to do next and how we're going to make sure that the wonderful services that we've been providing will continue, and will continue to serve the nation in the right level of architecture and technology and ground systems. So first, explain what we're talking about. We have a vision in NESDIS to develop a deep, integrated, data-driven digital vision or understanding of the planet, and and the changing planet at that. So it's a very important vision. It involves obviously not only flying satellites, not only building and developing and flying very advanced technology satellites, but also having the ground system to support those satellites, getting data from our partners, both our interagency partners as well as our international partners, because they're also flying environmental satellites. And it's a job that creating this vision of an integrated digital world cannot be done by one country alone. It really comes through collaboration and partnership with a lot of other countries and agencies. And of course, having the tools and having the systems to be able to take all that data and turn what you might call raw satellite data into really meaningful data, products, and services. So all of that is the role of NESDIS, and we'll talk about that today, although I lost the presentation. Oh, okay, so now we're seeing the scope here. I'm going to show this video first, if you would. Play this video.
Hi Vanessa, I'm sorry, this slide, we've tested it, it worked before. I think there's some kind of burden with so many people online it's not showing. Do you want us to keep trying to move it forward?
Oh,
there we
go. Past the video, that's fine.
Okay, I'm sorry.
Post it online, people can download it. It's a wonderful video. It talks about how we're doing what we do with the environmental satellite business. But yeah, let's get that kind of video. Video, and we can make it available online, so you can download it if you'd like to see it. But luckily our satellites work far more without some interruption. So first I want to talk about NESDIS, which is the NOAA Environmental Satellite Data and Information Service, and fit in the context of NOAA and the other NOAA line offices. So we're one of the two, if you might say, cross-cutting line offices that provide the tools, the observations that are used by the other line offices to meet their NOAA mission requirements. So we're down here at the bottom, Satellite Information Services, and of course we support all of the other NOAA line offices. We provide them the satellite observations, the data products, the application products that they use in their daily operations to guarantee their mission and continue doing their services. NESDIS is of course something we talk about from space to ground, and in this case, space almost to the surface of the ocean, the ground of the ocean basin, because NESDIS provides secure and timely access to not only our global environmental data, but as I mentioned earlier, the data from our international partners and our interagency partners, including NASA, in an integrated digital fashion. So we provide access to all the data that you can use and combine, and we do that in combinations, create those specialized science products in support of the NOAA mission, and of course then we archive that data along with a lot of NOAA's other data. The National Center for Environmental Information archives and stewars that data, and that's where we talk about from the bottom of the ocean to the top of the atmosphere approach. And of course now it's even out to the sun, because we have a focus on space weather that we'll talk about. This is the video I was talking about. I don't know if the globe is going to work. No, normally this is a really wonderful globe well, but it makes the point that measuring the environment and observing the environment is a multi-satellite, multi-themed approach. We have to look at all the different themes, all the different areas of the planet, the land surface, the cryosphere, the ocean surface, the ocean depths, the clouds in the atmosphere, the weather, the space weather events. All these things are observed by satellites. We combine that data to create this integrated digital understanding of the Earth system. OSAP, of course, has a huge role in that, because we sit at the center of NESDIS and are responsible for two things primarily. One is setting the strategy and the architecture for where we're going and what we're doing with our environmental satellites, ensuring the consistency of how we approach the problem. We have many large programs in NESDIS, including the GOES-R program, the JPSS program, other programs that will be developed over time. But we have to make sure that the work that they do and the things that they take on in their endeavors are consistent, and the processes that we use are consistently applied. So we have a strong role in the systems engineering aspect of the Satellite Information Service. Part of that system engineering aspect is to set requirements and prioritize all the things we need to do. There are so many things that we need to do, so many needs from the line offices, and we often have to make choices about what we do in the near term, what we can push off, what we'll do over time and develop, and that prioritization is a key part of the activity that my office organizes for NESDIS. But again, it's not something that we do alone. We organize it, we execute the process, but we use representatives from all the line offices to help us make these decisions. It's a very much a process where we reach out to the users engage the users, not only in the NOAA line offices, but external users as well, to understand what their needs are and understand what we need to do in the satellite development to meet their needs in the future. And of course, communication is a huge piece of that. So we have liaisons to other organizations, technical liaisons to the program, to outside our organization, to other agencies and international groups working on similar problems, as well as validation. Again, this is a role of engaging the users and involving the users to understand that the things that we're doing will actually meet their needs. So we validate that the requirements were correct, and as we develop these systems and start flying them and operating them, that we validate that it did meet the user needs as we planned. So big responsibility. We're involved in this, but mostly we're really involved in the architecture, and that's what we're going to spend time talking about today. But why does all this matter? Why does environmental satellites and weather satellites, why does the nation really need to focus on the continuation of these important observational platforms? This slide produced by our NCEI, our National Environmental Center for Information in Asheville, North Carolina. We do this every year, and we look at the number of weather and climate extreme events that cost the taxpayers across the nation over $1 billion. So the response to the reaction, the damage, the property damage, again, for each of these incidents equaled over $1 billion. We had 16 of these incidents in 2020 thus far. And this is a calendar year, so it's not even, we haven't even reached the end of the calendar year. But you can see these, I like to say this is, incidents from fire to ice, from drought to precip. So we have flooding incidents that cause major flooding, whether that's related to tropical storms arriving on, landing on the coastal areas of the U.S., whether it's, torrential rainfall and heavy precipitation events. The flooding often creates these billion-dollar events. And of course, we have drought events that cost money. We have severe weather events. So this is a chart that basically shows that. And in fact, 2020 was a very, very big year. And we've had a lot of these events. It's not the biggest year over the last 5, but it's one of the highest ones on record. I'll give you some examples of how we use satellites to observe these extreme events. This is a case where an ice sheet collapsed in Canada, the Milne ice sheet. This actually is using Sentinel data. So I talked about using data from our partner satellites. Sentinel satellites are created or built by the Europeans. And so we get data from them and use that in our daily operations. So this shows the collapse of Canada's largest ice sheet. In this case, the collapsing area that was forming an iceberg now is larger than the whole island of Manhattan. That happened back in early August. These are all very recent events. A week later in August, we had a derecho, remember, coming through Iowa. And there's been pictures that we posted on our social media sites of the damage this derecho did over Iowa, where entire cornfields were just flattened by the wind speeds that were in excess of 100 miles per hour as it came across Iowa. And of course, what you can't see, we had this in a video loop, but we weren't able to show it. These bright spots on the image are lightning. This is lightning from our global lightning mapper on our GOES East satellite, so that we combine the visible and infrared imagery with the lightning to really show where the storms are, how they're developing, and how they're being transported across the planet, across the CONUS. We had a very active, as you know, tropical season this year, and this is an example of a tropical storm. In this case, tropical Hurricane Laura, that went from a very weak Cat 1 coming out of the Caribbean to by the time 18 hours later, it made landfall in Louisiana as a Cat 4 storm, so rapid intensification. So satellite observation, satellite information, and data provides us what tools that we can use to model this intensification and do a improved job in the future of forecasting these type of events. This is a chart. We originally had a bigger picture that showed the whole Atlantic and Caribbean basin, but at one point this year, and I think it was early September, we actually had 6 named storms in the Atlantic and the Caribbean. And to my knowledge, that's the first time I'd seen that many storms at one time present at under the same, certainly the same picture on a satellite imagery. And of course, we have fire. So we talked about fire to ice. We have the ice incidences in Canada. Here's an example of an extreme event for fires. Satellite and satellite data has become a really beneficial tool for fighting fires, for identifying new hotspots when they arise quickly. So it gives us a very first indication of a new hotspot developing, and the people doing the firefighting, worrying about this, can go respond accordingly before new flare-ups become larger. So this is, as you know, has been a very active fire season in California and Oregon and other places in the West. And of course, our satellite data from our GOES East and GOES West satellites is an important source of information that is used to fight those fires. So it always helps to talk about where we are today. So if you look at this, we have two constellations today of weather satellites, atmospheric satellites. One is our GOES-R constellation, which is in the picture here that I've highlighted with the arrow. And the down below is our JPSS satellite. These are very capable satellites. These are large. We've developed them over time, and they provide a lot of capability with a lot of instruments on board the satellites, co-measuring things. In the case of GOES-R, there's a visible imager that looks down at the Earth's surface, watching the clouds, the environment below the surface. There's also the global lightning mapper that I talk about, and there's a number of space weather instruments that actually sit out here on the antenna, on the yoke of the antenna out here, that actually measure space particles, the magnetic field around the satellite, as well as imaging of the sun and events on the sun that will cause geomagnetic storms. It could cause geomagnetic storms later in the week. This is a very capable system, as I mentioned, with these large, very capable satellites. However, these satellites are very expensive, and because they have multi-instruments on board, because they're designed with the lowest risk, in some cases the lowest risk possible, to ensure the highest level of assurance on these satellites so we don't have a failure on orbit. Because of the way we designed those in the past, we started designing them, and in some cases, in the case of GOES-R, we started 20 years ago designing the satellite, designing the instruments, looking at what we would do. And we plan to do block buy, so we buy up to 4 satellites at a time, or in a row, with the same instruments and the same technology. That's a very useful thing as far as developing the science algorithms that go with it. But it does mean you're sort of locked into the technology for a long, multi-decade time period. So you're locking up not only your funds, but also you're locking up your technology. So it's not very flexible. It's very capable, but not very flexible or adaptable. So as we plan our next generation of satellites, we're looking to improve, to bring more adaptability and flexibility into the system. Let me get this arrow out of the way for you. So as we've designed our system, we basically are looking at what we call 4 pillars for our strategy for our next generation of satellite observations. 2 of them are pillars based on the orbit geometries in which we will operate those satellites. One is low Earth orbit. These are satellites that orbit the Earth in sun-synchronous orbits, as well as some mid-inclination orbits that aren't sun-synchronous. But they're close to the Earth. They're about 800 kilometers up, 500 nautical miles. Because they're close to the Earth, they have great spatial resolution of the events they're watching. And of course, they're circling the globe, so they allow us to get a global look at what's happening. We get to see global data. The data from these these polar orbiting missions and these low Earth orbiting satellites, it's what feeds the numerical models. It goes into the environmental models that do our numerical weather predictions, as well as our ocean models and other models. On the GEO orbit, this is from geospace orbit, much higher up. Because of the GEO orbit, we can monitor the real-time weather conditions, see the things that are happening in real time. And you've seen wonderful pictures. We've seen wonderful pictures from our GOES-R satellites in the GOES East and GOES West positions of tropical storms and tornadoes and other formations, where we can get an image every 30 seconds and can track what's really happening in real time below the satellite. And then we have another pillar that's in space weather. This is to continue the measurements we've done over time. We've been doing space weather measurements for a number of years, but this is going to be a focus on how we do space weather regardless of orbit, whether it's in the GEO orbit or a low Earth orbit or even an orbit out in the Earth sunline like we have today with our Discover satellites. So as we move into the strategy of these futures, we're going to take advantages of technology development in order to create, as I talked about, that increased capability and flexibility. This is especially important for our low Earth orbiting satellites. We're looking at doing things quite differently in the future than what we've done in the past. In this case, we're looking at what we call disaggregation. That's not putting as many instruments on a single large satellite, but rather putting those instruments on smaller satellites, 1 or 2 instruments on a satellite, those satellites will be much more affordable, lower cost than what we had in the past. The instruments themselves, we're looking to miniaturize the instruments, make them lighter, require less power, require a lot of less capability, but still overall meet the same capability we have today with our current satellite systems. Because these things are more affordable and because we're putting them on multiple satellites, when we have a problem on a satellite, it's going to affect only that one instrument perhaps, and we'll be able to rapidly, in a few, put another satellite up to take its place. We really don't have that capability today. Today we have to create that reliability by having an extra satellite in space in case the primary satellite should have a problem. We're also looking at what we call proliferation of satellites. So because we're going to smaller satellites that can be launched on smaller launch vehicles at less cost, we're looking at perhaps having more observations around the clock. So we're today with our large satellite program, we get about an image all across the globe about every 4 to 6 hours. So anywhere in the globe you'll see an image about every 4 to 6 hours. Well, by going to smaller, more affordable satellites, we can launch more satellites, and we can put them up at different times a day. So now we can get the refresh time down well below that 4-hour period, allowing us to have more data going into the models around the clock, which is what we need to do, especially for our regional models, like our hurricane models and our regional weather models. They want to run those models. They need to run those models far more often than they do today with the big global models, and they need the most recent data they can have to drive those models. So that's what we're looking for on the LEO side. And because we're taking advantage of what's happening in the satellite technology sector, not what we're developing, but what the commercial sector itself is developing with these small capable satellites with interface with small launch vehicles. We're taking advantage of all of that and creating our plan for our next generation LEO satellites. On the GEO side, we're taking advantage of technology and coming up with imagers and instruments that are at least as capable and more affordable because they can be made a little smaller, a little lightweight. But the problem is, when you're looking at the Earth from that high up, it takes a very large instrument with very large optics, with very large mirrors, lenses, and so it takes a pretty large instrument. So what we're going to do in the future for our GEO Exo program, and GEO stands for geostationary orbit, Exo stands for highly elliptical orbits, which we're also looking at doing things, which allows us to do measurements over the poles, over the North Pole, that are similar to the measurements we make today over the CONUS with our geostationary satellites, which are stationed over the equator. So we'll have that same capability of near real-time imaging of the polar region of the Arctic Ocean, the Arctic land masses, 24 hours a day. So that's what we call our highly elliptical, highly inclined orbits. But the instruments, and we're also looking at adding new capability that we don't have today. We're looking at making new measurements that we don't currently make. Measurements like ocean color, which is something we make today from our low Earth orbiting satellites, but we've never been able to do from a geosynchronous orbit before. So we're looking at that as part of our planning. And then I mentioned space weather. Again, we're looking at a comprehensive measurement program for space weather, understanding what's happening on the sun, understanding how it's interacting with the Earth's atmosphere, the ionosphere, the thermosphere, as well as lower things. All three of these approaches, however, requires a very capable ground system to support them, whether that's to operate the satellites themselves. As the Admiral talked about, I was in charge of satellite operations for a number of years for NOAA. We have to have very competent systems to operate those satellites, but also to do the very important job of taking the data from the satellites and turning it into very useful scientific information, application services, information about the planet, about the weather, about the climate. All these things that we do are important, and we have to have a ground system that's very capable to do that. So we're looking to develop a new next generational ground system that's very scalable, that's very adaptable, that's very fluid. As we talk about, having the ability to make changes quickly, to add capability when we need it, to reduce capability when a need goes away. All these kind of things are now available based on the technology that's available out there today in the IT world, in the ground system world, using things like the cloud and other techniques. So how are we going to do that? Here's the timeline, if you will, for what we're looking at. So as we started looking at developing our satellites, we looked at, back in 2015 to 2018, looked at what we call the NSOSA, which was the Satellite Observing System Architecture study that we did. And we looked at what observations NOAA needed to make in the future and looked at the value of making those observations in the architectures, the satellite architectures that would allow us to make those observations at the lowest cost, or the highest value for the lowest cost. And so we did a study. We finished that study in 2018. And then starting in 2019, we started the implementation of that NSOSA architecture. So we can call it post-NSOSA, if you will. We started that by going out to industry. We went out to industry in 2020, early in the year, and we have 32 companies and academic institutions performing what we call broad agency announcement studies. These are concept studies of missions, instruments, how you would package instruments on these, in some cases, disaggregated or proliferated satellites, how you would be able to operate these things, looking at different business models for how we acquire data, looking at commercially acquiring data, looking at rideshare opportunities where we would build an instrument that we would fly it on a commercial satellite. They would fly it for us. They would launch it and operate it. We would just provide the instrument. So different business models. So like I said, we have 32 of these studies underway. They're coming close to the end now. We expect to have them all finished by the end of the calendar year. And we'll take that data then as we move into the next year, into 21 and 22. We'll take that data and we'll use it to plan out and start developing and designing the next generation of systems, our GEO Exo systems as well as our low Earth orbiting weather satellite systems. The first of those we're going to look at is a LEO, we call a sounder sat, which is an instrument or a mission that will measure the three-dimensional components of the temperature and moisture fields in the atmosphere from the top of from space down to the ground. This is a very important measurement that's needed for a lot of activities. Numeric weather prediction, of course, we do that today with our low Earth orbiting satellites, but there are other opportunities as well of measuring those vertical state of the atmosphere. So we're having a LEO sounder set. And then as we move into the late 20s, we'll have our first launches. So as we look at these new approaches, including disaggregation and proliferation, we want to test out that capability. We want to test out whether smaller instruments flown together can create the same capabilities that we do today with our larger satellites. And so we're going to have prototype pilot demonstrations and opportunities starting as early as 2026 with the first demo flight of a LEO sounder set. On the GEO Exo side, we pretty much have enough satellites in place or currently being developed. We have 2 more satellites being developed to launch and operate. That'll take us into the mid-30s. However, our operations concept for a geostationary satellite is to have one very capable satellite in the east, a duplicated satellite in the west measuring the western United States as well as the Pacific Ocean. The one in the east, of course, measuring the Atlantic Ocean and watching for tropical storms and other things in the Atlantic Basin. And then we have one storage satellite that's stored on orbit in the middle of over the middle of the country in order that it can be moved quickly to take the place of either the west or the eastern satellite should one of those fail. And so we have 3 satellites in orbit. So when we get below 3 satellites, we have a plan when our timeline says that we won't have 3 satellites operating any longer. We need to have a replacement satellite in place at that time. So in the case of geostationary satellites, that comes in around 2030, 2031. So our GEO Exo program is designed to have an operational satellite launched and in place in 2031. So this is sort of how we're going, that's what we're going to do, that's the timeline, and this is how we're going about acquiring those satellites and doing that satellite development. Number 1, we're looking at new business models. We talked about commercial data buys, so buying the data commercially where we can buy the data as opposed to building our own satellite, or working with our international partners to get data from them that they're flying in different orbits or different instruments. If they're going to fly an instrument that we can use that data rather than build something on our own, that's our first choice. We also have our joint venture business model, which says we're going to team with NASA and DOD and industry on technology development, to take technology that they're developing and make sure it can be used operationally on NOAA satellites in the future. We're also, of course, as I mentioned already, taking advantage of opportunities that's out there from the commercial satellite sector. So they're developing small instruments. They're developing small satellites. They're developing how to launch and operate multiple fleets of satellites, if you will, swarms of satellites. All that is technology that we want to leverage and take use of in designing our next generation program, because that makes getting things into space more affordable. It allows us to, as I talked about, having more satellites around the clock, a proliferation of measurements, and so that's important. And of course, I'm going to talk about at the end of my talk the ground and data system that we need to support all the satellites that we'll be building and flying. And of course, partnerships, as I mentioned, with private industry on the commercial data buys, with other agencies and our international partners, all with the goal of getting this integrated digital data set across the globe. And of course, most important of all of this and underpinning all of this is engaging our users. So it's an important thing while we're having conversations like we're having today about basically letting our users know what we're doing and getting their feedback, getting their comments. And we have a very far-reaching plan of engaging the users, and I know one of the poll questions relates to that, so I encourage you to take the poll and give us some feedback on how our user engagement, reaching out to you and talking to you about what we're doing, getting your needs, getting your understanding of what the things you're going to be doing in the future and how you visualize using satellite data in your operations. So let's talk about the two things that I've already mentioned most of this. First is GEO Exo. As I mentioned, the GEO Exo satellite is going to be very similar in a lot of ways to what we've flown today with GOES-R. We are looking at making things smaller where we can. We're looking at adding new capabilities, new instruments that we have not flown before, an instrument to do an ocean color measurement, an instrument to do an atmospheric composition measurement, things we have done perhaps in low Earth orbit, but we've never tried to do in geosynchronous orbit. Doing it there, of course, gives us that 24/7 capability of monitoring things in real time that we currently can't do from LEO because we only have a satellite crossing over every 4 to 6 hours. We're looking at hyperspectral sounding, something we've talked about for many years about having a hyperspectral IR sounder in geosynchronous orbit. And this allows us to really understand and characterize the environment around severe weather, especially in the center of the United States and other activities as well. But this is a very useful instrument that we're now looking at trying to fly as part of our GEO Exo program. We're also continuing to look at space weather data and how we can acquire new information, new observations that we do not currently do today. An observation like an auroral image, having a camera. We talked about having highly elliptical orbits. Having an auroral imager on one of those satellites in that orbit, it allows us to monitor the auroral output in both poles, in other words. We're looking at things like, having standard satellite buses. This is how we make things more affordable. Using smaller satellites where possible, perhaps where possible, for space weather instruments, flying things on space weather instruments on smaller satellites with less launch costs. Hosting services, I talked about that, hosting our instruments on commercial satellites. And of course, looking to what we can buy commercially. Commercial data is a growing sector for the nation. We are currently, as the Admiral mentioned, starting our first commercial weather data buy. And I'll talk about that in just a second. But this is an area where we expect to continue to see growth and availability for us to buy data as opposed to building instruments or flying them on government satellites. SounderSat we've already talked a lot about, but I will say that the studies that we're doing really relate to, again, commercial services in some cases. Multi-orbits, how many satellites would you put? How many different orbits would you put them in to create the coverage over the globe that you would like? How many satellites would it take to have, say, hourly coverage over the entire globe or 2-hourly coverage? Something, much shorter time frames than what we have today with our current technology satellites. Looking at rapid launch cadence. How can we launch things on 3-year centers or 5-year centers so that every 3 to 5 years as we're launching if we're planning to launch the next satellite, build and launch the next satellite, we can make those technology changes that I talked about. We can create that flexibility and adaptability and make changes. We're not pinned into a technology for 20 years or 30 years. And so that's an important part of our approach to the LEO satellite program. Check how I'm doing on time. I think we're doing okay. And I mentioned space weather. This is, again, we've been making space weather observations for a number of years from all of our satellites, from our geosynchronous satellites as well as our older POSE satellites or polar orbiting satellites. And we have our Discover satellite out at the L1 point, which, if you know what the L1 point is, it's a point between the Earth-Sun line that's about 1 million miles from Earth. So it's 1 million miles closer to the Sun than our geosynchronous satellites are that are in Earth orbit. So it allows us more lead time of seeing things before they arrive and before they hit the atmosphere and can cause problems that we need to provide warnings. So it's a key system, a key observational platform, early warning system used by the Space Weather Center, the Weather Service, to make their warnings of space weather events. We're looking at other opportunities as well, observing the sun from other off angles, from L3 and L5, which are other points between the Earth's sun, where the gravity, where it's easy to put a satellite, or easier to put a satellite up and operate it. We're also looking at other things as well, and looking, as I mentioned, at small satellite capability and other opportunities. Oops. So going quickly, this is a joint venture. I talked about a little bit about how we're going to do technology development and how we're going to team with our partners, our other partners, on doing technology development, where they may be developing technology to get it to, say, early technology levels, where they built an instrument or they tested it in the lab. We can collaborate with them and fund the act of getting that technology perhaps into a space demo, and to demo that in space to see if it works, in a flight opportunity. Also, making sure that the technology as it's being developed will meet the needs of, can meet the operational needs of NOAA and our missions. I mentioned commercial weather data. We currently are evaluating proposals for our first commercial weather data buy, and we expect to award contracts very shortly to firms who can sell us, in this case, what we're calling radio occultation data. And there's an image here of how that, what we mean by radio occultation data. But again, it's a way of getting a vertical profile of the atmosphere using the signal from a GPS satellite and an instrument on another satellite, and as the satellites basically descend through the atmosphere, the line of sight between the thing descends through the atmosphere, you can measure the temperature and moisture profiles. We also have recently issued a new data pilot RFI, a request for information from the commercial sector on what they may be looking at doing in the future, so we can look at other opportunities to buy data. And of course, I wanted to talk a little bit about the ground system, as we need a very competent, as I mentioned, agile and flexible ground system to support the satellites that we'll be buying and flying. This is how we do it today. It's a very stovepipe system. We have a satellite, we have a ground system that gets the data from that satellite, we have a processing system that does the data products from that satellite, and then we provide it to users. Well, now we're looking at something that's far more enterprise in approach, a system that can take data from all satellites, securely ingest it, do the processing, turn it into useful products, make the data available via the cloud to users who can come use the data directly on the cloud, or can download the data from the cloud and get data into their system. So this enterprise ground system is going to be a very vital part of what we do in the next generation of satellites and ground systems. This slide talks about that. Basically, we're looking at three components of an enterprise ground system in the future. One that handles satellite operations. This is how we actually do the communications with the satellite, the command and control, the C-cubes, the mission operations, all the things we have to do to control and operate our satellites. Once the data is on the ground, then we have science operations. This is applying algorithms to the data to create useful science products. And then we have data operations. Data operations basically is taking that data that we produce, those science products, the applications and the services that we create, and making them available to the users like yourself, getting you involved, trying to figure out how to get the data to you in the best fashion and with the lowest latency, or at least with the latency to meet your requirements. Talking about then using that data and stewarding it, archiving it for long term, and doing the data stewardship that's necessary to make sure that data is useful for climate studies and other analyses beyond what we do with directly with the satellite data itself. So this is our approach. We're actually doing an enterprise study, similar to what we did with the flight systems back in 2018. We're doing it now with the ground systems, and we expect to complete that study by the end of this year. So by next fall, we should have an understanding of what the architecture is going to look like for a ground system in the 2025 to 2030 timeframe. And this basically talks about that as well, about how we get to that next generation information system that we need to have in place by 2030. And we started by doing some early cloud piloting. We worked with Amazon Web Services and some other companies to try to figure out how we could do our data job, our data processing using cloud-based systems, using a cloud-based architecture, and looking at things like, can it meet the latency requirements? Can it meet the data quality requirements? And we actually have our first operational cloud-based systems in place today. And this is our secure ingest. It's bringing data in from our international partners, as well as we'll be bringing the data in from these commercial, on this commercial weather data buy when we award those contracts. Bring it into the cloud, doing searching on the data to make sure it's safe to use in our systems, and then starting to process the data. That process will continue to go over the next 6 years, 7 years, and by that time we will have been able to move all of our current on-premises, we know that term on-premises IT systems that we use today, all those stovepipe systems, to a cloud-based architecture. And of course then we focus on how that architecture will need to evolve and be enhanced over time to meet the needs in the 2030 timeframe with these new satellites that probably will be producing far more data than we produce today. As I mentioned, underpinning everything we do is our user engagement plans and programs. And so we start by reaching out to the users, understanding their needs, going out and really sitting down with them, not just sort of having them answer surveys, but sitting down with the users and saying, show us what you do, or show us how you do your job, and how you use satellite data, and how you're thinking about using satellite data in the future, and what do you need to do, and what kind of products would we produce that would make it easier for you to get your job done, to meet your mission requirements. We, of course, have other things. We have agreements. We have U.S. law. We have a lot of things we have to adhere to, policies and other things. That all goes into what we've called our NESDIS level requirements. And this is a new approach we have to meeting our NOAA, the requirements we have coming down from NOAA for NESDIS to operate and NESDIS to implement. So we created this NESDIS level requirements. We vetted it with the users through the NOSC, which is the NOAA Observing Systems Council. And of course, we're finally getting ready to have those requirements signed off. But those are not static. They don't just sit there and never change. We have a process, again, using user engagement, of where we evaluate those requirements, how we bring user input into that, how we make our strategic decision making based and that needs to change those requirements. And then, of course, all that then flows down into the programs and projects to tell the program directors what we need them to implement, what they need to go do, what they need to go design and build, or in some cases buy if it's commercial data, or barter if it's an international partner. How we go get the data that they need. We tell them what products. And what's really important in all of this is we're going from a strategy of not of requirements for the satellite itself or the instrument, although we'll still have those. We have to have requirements, obviously, to design and build something. But at the next level, we're focused on the observation. We're focusing on continuing, making sure we have continuity of those critical observations that we make today, whether those are observations of the weather or the storms, tropical storms, intensification of hurricanes, fire products that are used to do the fire weather mission. We want to make sure we have the continuity in the continual production of those products and have a plan for replacing the current satellite technology or the observations, the data used to create those products from current satellites with future satellites. So we have a plan to make sure that we'll be able to continue to produce those products. And that is, again, a big part of our process. And then, of course, we also have to have a plan for implementing and creating those products and then doing the stewardship. Very important piece, the archival and stewardship of those data at our NCEI and in other places, just to make sure that those data products are useful to the broader community, not just the NOAA community, but the broader community as well. All right, so this is the last slide I think I have, but just as a summary chart, again, what are we doing? We're obviously working on a plan and planning and implementing our next generation of Earth observation and data systems to meet our architecture that we designed back in 2018. We'll have delivery of our space-based satellite observing systems starting in 2026, but of course the real need dates are in 2030 to 2050. So we're planning a 20-year program of satellites and ground systems to meet the NOAA needs through that 20-year period. We're looking at using joint venture, we're teaming with industry, teaming with other agencies, international partners, or industry in this case, not international, but industry, to create and develop the technology we'll need to be successful. And then we're doing, looking at using BAAs, other things to help have industry help us understand and plan for these missions and develop the concept for this new approach. And of course, we're expanding our space weather observational program to look at a very totally encompassing program of measuring the space weather inputs and observations. We're leveraging, as I said, commercial and international partnerships. Our first data buy is the contracts will be issued shortly, and we'll start buying data commercially for use in NOAA's weather models. And of course, we're adapting the emerging technology through our joint venture program that I talked about. So I think that may be my last slide. Yeah, I did want to thank all the people. Thank you for listening, of course, and going to take your questions now. But I want to acknowledge that this has been a huge job by a lot of really dedicated people, not just in NESDIS, but across NOAA and outside NOAA. But all the line offices have had a really large role, and we really appreciate all the support we've gotten from the users, from the NOAA users, and the NOAA other people that are that are looking at what we're doing and want to get their needs met. And of course, we're relying on working groups of users to help us continue as we move out and start implementing this program then to benefit both today's world and the world to come. So and here's a place you can send questions. If you have questions later, you can send it to this address. But of course, we'll have a few minutes now to take questions from you directly. So thank you.
Great. Thank you so much, Vanessa. I don't know how you hold all that information in your brain. There's just so much to take in. I was overwhelmed. Great presentation. Thank you. So we will start our questions today with Kate and Frank moderating, and they'll be reading them to you. And while we're doing that, we're going to have a few polls running. So folks online will run each set of polls. There's 4 poll questions. We'll run each for about 2 or 3 minutes each. Okay, thank you. And Frank, you'll begin with the questions?
Yes, I will. The first one is from Dave Lubar. Vanessa, how do you see our partners in CGMS reacting to changes in the availability and complexity of the radio frequency spectrum that is so critical to the operation of our satellites?
Thanks, and thanks, Dave, for the question. That is an issue that we're working at all levels with our partners, especially our international partners. That's in, he mentioned CGMS, which is the Coordinating Group on Meteorological Satellites. This is an international group that's been in place for many years now, looking at how we develop and plan and operate meteorological satellites. And of course, radio frequency interference is a key issue for anyone operating meteorological satellites. As you know, we have the issue of the 5th generation or the 5G interference with some of our measurements of our microwave instruments, because and we're looking at how we can mitigate that. But we support and we work in international collaboration with the other international organizations that are looking at radio frequencies, looking at spectrum management. So it is a very key topic that is discussed at all levels.
Vanessa, this is Kate. I've got your next question from Steve Moran. Hi, Vanessa. Thanks for taking the time to present today. Can you tell us if there will be additional opportunities or on-ramps for the LEO and GEO Exo industry concept studies?
I can't say for sure, Steve. I will say that we'll be working this year on sort of thinking about what comes after LEO SounderSat. We know that's the first of the weather satellites that we'll be developing. And so we'll be looking at other concepts for things like ocean color measurements or day-night band, low visibility imaging, precipitation measurements. We'll be looking at a lot of other things that we want to do, and we will be issuing a lot of concept studies as we go through that process. So yes, I think there will be other opportunities for on-ramping for other things. On the SounderSat site itself, I think we'll probably take the data that we've acquired from this current set of BAAs, and we'll be looking at that to see if we have what we need. But we'll probably take a similar approach to what you're seeing on the GEO Exo side, which is they're going to let some contracts for some more detailed studies than what we did with the BAAs, and we might do something similar on the LEO side. But again, no decision's been made yet.
Okay, thank you. The next question is from Paul Hepner. Can you comment on any lessons learned from GOES and JPSS for the next generation satellites?
Well, I mean, lessons learned. Obviously, the value of those satellites is clear, and having a capable system is very clear. One of the lessons I think we've learned is we need to come up with a better approach for making sure the users are ready to use that data. when we launched the satellite. So I think that was something we started with GOES-R and adapted for JPSS. That's worked very well. We've done a lot of preliminary work with the operational groups to sort of show them the capabilities that they're going to be seeing and to develop tailored algorithms for their use of how they're going to use that data once we go into operations. That's allowed us to get systems into operations much faster than we ever did in the past. That'll be very important, especially on the LEO SounderSat or LEOSat. As we go to smaller missions that, the satellites themselves may only have a 5-year life as opposed to, right now our systems are designed for 8 to 10-year operational lifetimes. If we go to shorter lifetimes, it'll be very important to make sure we can use that data right away and we don't spend, months to years before that data is able to be used, in our numerical prediction models or in our operational concepts. So I think that's an important lesson that we developed and learned on JPSS that we're adapting and will be using as we go into the next generation. Calibration obviously is a big thing as well. Obviously, that we have, the data quality that in our satellite data is the most foremost concern to everybody. I mean, we have highly qualified, highly capable data. The data is well calibrated. It's so, and you can count on it. It's dependable and it's available. The reliability and availability are both there. These are all things we have to still maintain that capability as we plan the future. We may do it in a different way. We may calibrate satellite data in a different way than we do today, because that having some of the onboard calibration, it's costly and it takes space on a satellite. So the instrument's got to be bigger. So in some cases we're looking at alternatives, but we will do everything with with the full knowledge that we have to have a fully capable system.
Thanks, Vanessa. The next question is from Bob Atlas. Are there any plans for LiDAR wind profiles from space?
No defined plans yet, Bob, but we are looking at that. I mean, 3D winds was one of the top measurement observational requirements coming out of the NSOSA study. If you look at how they prioritize all the observations, 3D winds was at the top of the list. Now, of course, there are a lot of different ways you can do 3D winds, and this is, for those that don't know, it's being able to understand the winds through the atmosphere. Right now we can do it at 3 or 4 levels using our geostationary satellite data, but we want to be able to do wind profiling, with far more levels in the atmosphere. That they see that as a real, a thing that will have really large impact on the accuracy of the models, on the prediction skill, performance skill of those models. So, but there's ways to do 3D winds. You could do it with passive techniques as well as active LiDAR techniques. And we'll be looking at both. We'll be part of there's a wind LiDAR workshop just next week, and I'll be talking there and getting ideas. And of course, we've done a lot of preliminary work on doing some of the modeling of how you would use LiDAR winds in our process and in our products.
Thanks, Vanessa. Next up, a question from Steve Goodman. Is NOAA having conversation with other line offices on how in-situ measurements complement or may be alternatives to satellites? For example, the NRC, the National Research Council, looked at land-based profilers in lieu of or in addition to satellite sounders for high resolution in the boundary layer.
Yeah, Steve, that's really a question I would like to get back with you on. I mean, I think that's a question for Mitch, who's our senior scientist at NESDIS. I think those conversations have been occurring, and of course as you know, that there's a new structure at the national level on ICAMs, and one of the things that ICAMs is looking at is how we integrate observations both in situ with satellite data as well. So I think the conversations are occurring, but I would refer you to Mitch, and I'll have Mitch call you if he can give you an answer there.
Thanks, Vanessa. The next question is from David Kalin. What is OSAP's plans for further systems engineering support, and how can industry?
Well, yeah, I can't talk a lot about some of that, because that's a question of procurements and things. But we definitely, see the need to have continued system engineering support. It's something we have a very competent staff of people, federal civil servants and others. But we get all of our support. We get so much of our support from either our support contractors or our industry partners. So yeah, we will clearly still need that that engagement will still need that level of effort as we move out on the system engineering side. So you'll hear more of that as we go forward.
Thanks, Vanessa. The next question comes from Ed Baker. Why haven't we partnered with the Canadian Space Agency for a high-latitude ground station when FCDAS only sees 12 of the 14 daily orbits and Svalbard and McMurdo are so much more remote?
That's a good question. We did partner with them in the past on like RadarSat and things and got data from their ground systems. And of course, they do get a lot of our direct broadcast data from our satellites and use it in their operations. We have a strong collaborative, partnership with Canada, and I think we'll continue to talk about that. One of the things we're talking about is, as I mentioned, these highly elliptical orbits. I mean, one of the things we're looking at is they have the same needs, so we're looking at other areas where we could collaborate as well, and that could also involve ground systems. But as far as the polar ground systems that we have today, between Fairbanks, which as you mentioned only sees 12 passes of a sun-synchronous satellite a day out of 14, but Svalbard sees all 14, and so we have we back up our Fairbanks operation with our commercial capabilities from Svalbard, as well as even from our other ground systems that don't see as many passes, but may catch an orbit that Fairbanks didn't see. And of course, we also have ground capability now in the Antarctic, and so we're trying to create data as we move out in the future with JPSS-1 or JPSS-2. We'll be looking at having half-orbit coverage and collecting data every half-orbit using our McMurdo ground system as well as our Svalbard ground systems and Fairbanks ground systems.
Vanessa, this is Sandra, and I'm told that that is your last question. Is there anything else you'd like to say to our audience before we wrap it up today?
Well, again, I hope you fill out the survey. I'd like to hear more about each of you and what your interest is. But again, I'm excited. It's an exciting time, and we're very excited about building the next year satellites, and we need your help, and we'll be talking to you.
That's great, Vanessa. Thank you so much for a terrific talk. Folks, I want to thank you all for attending and joining us today, and to let you know again that the next seminar in the NOAA Environmental Leadership Seminar Series will be on Tuesday, December the 8th at 2 p.m. Eastern Time, featuring Admiral Timothy Gallaudet, Assistant Secretary of Commerce for Oceans and Atmosphere and Deputy NOAA Administrator. Please join us then. Thank you very much for attending, everyone. Thank you very much, Vanessa, for your comments and your talk today. Great talk. Bye, everyone.
Bye-bye, everyone. Bye-bye, everyone.